Hello and welcome to the AI Research Roundup. I'm Alex, and today is May 7th, 2025. From Hugging Face's trending list, published just 6 days ago, we are looking at this paper, a robust deep networks-based, multi-object, multi-camera tracking system for city-scale traffic. It tackles multi-object, multi-camera tracking, or MOMCT, that is, following many vehicles across different city cameras, even when their views do not overlap. The authors propose a deep learning system using mask RCNN, a method that helps accurately detect and outline vehicles in video footage for this tracking. Alright, so this figure visually walks us through their proposed multi-object, multi-camera tracking framework. It starts with video feeds where mask RCNN detects vehicles. Then, non-maximum suppression, or NMS, filters out overlapping detections. Next, short vehicle paths, known as tracklets, are generated within each camera using an algorithm called deep sort, efficiently using visual data. For re-identifying vehicles across cameras, a ResNet model, a powerful deep learning network for image recognition, is employed. This re-identification is aided by an aggregation loss, helping the model learn better, and a distance matrix, which measures vehicle similarity. Finally, unique tracking IDs are synchronized. Okay, so this next diagram, labeled Figure 3, shows the data preparation and vehicle detection workflow in more detail. It begins with input from multiple cameras feeding into the mask RCNN for initial detections. You can see how it identifies vehicles like cars and buses. Then, these detections are sorted by their confidence score. Basically, how sure the system is about each detection. After that, additional non-maximum suppression is applied to refine these detections, removing overlaps, before the vehicles are finally cropped out. This refinement is crucial for accurate tracking later on. Following the vehicle detection, Figure 4 illustrates how vehicle re-identification training is done. Cropped vehicle images are fed into the ResNet 152 model. Its output then goes through average pooling, a technique to summarize key visual features. This information helps calculate an aggregation loss, which combines two learning guides: triplet loss, teaching the model to group images of the same vehicle closer together than images of different vehicles, and cross-entropy loss, measuring how well the model predicts the correct vehicle identity. This process trains the ResNet 152 model to re-identify vehicles across cameras effectively. So, after training the re-identification model, we see its performance in Table 2. This table shows experimental results on a validation set that is a data set for checking model performance. It compares different backbone models, the core deep learning networks like ResNet versions that process visual data, paired with either MORT or deep sort tracking algorithms. Key metrics are IDF1, a metric balancing correct identification with track completeness, precision, the accuracy of identified tracks, and recall, how many actual tracks were found. The proposed framework with ResNet 152 and deep sort clearly performs best, achieving an IDF1 score of 0.8289, showcasing its effectiveness. Building on those strong performance numbers, Figure 8 provides a really clear visual demonstration of the system in action. You can see several vehicles, each highlighted with a colored bounding box, like a digital frame around it. Then, lines connect these vehicles from a main camera view to how they appear in other, smaller camera feeds shown below. This really drives home the system's ability to successfully track the same car or truck as it moves across different camera viewpoints, which is exactly what this multi-object, multi-camera tracking system is designed to do. Alright, and to further show just how well this multi-object, multi-camera tracking system performs, this table compares the proposed method against several other existing approaches. We are looking at the IDF1 score here, which, as we discussed, is a key measure of tracking accuracy and completeness. You can see methods like FiberHome, NTU, and KAIST scoring in the mid-50s, but the proposed method, well, it achieves an impressive 82.89%, significantly outperforming these others. This really underscores the effectiveness of their framework in these complex city-scale environments. So to wrap things up on this multi-object, multi-camera tracking system, It is clear the researchers have developed a truly robust deep learning framework. This system effectively tackles those tricky city-scale challenges, like vehicle overlaps and changing lighting, by using a sophisticated multi-stage approach for detection, tracking, and re-identification across different cameras. The impressive IDF-1 score we discussed really highlights its practical value for intelligent transportation systems. Thanks for tuning in to the AI Research Roundup, and I will catch you next time.